So that is scenario one. A 1G, 4,000 pound drop load, used a little bit of optimization, some motion, and we looked at our fatigue studies. Now, the next loading scenario that I would like to investigate is an impulse load. So our landing gear is stowed, and I'm making the assumption that there's nothing coming in and nesting the wheels so that they're just being held by the linkage. And we're going to apply a 20 millisecond sawtooth 20G waveform. And basically we hold the model at the mounts and we shock the system with our G load. And this is a nonlinear dynamic solution as part of simulation premium. The nice thing about SOLIDWORKS is that it's pretty simple to reconfigure our models. And since with our simulation tool, CAD is king, so it's not like we've spent hundreds of hours building an FEA model, and now we're going to change our geometry and have to go back and modify the elements and nodes. Everything is driven off of CAD and SOLIDWORKS, so we don't need to really change much other than just shift the positions of our models using our mate constraints. And if we built a simulation when the model is down or up, we can just copy between configurations. So I'm loading up a copy of the model with my Sim Premium simulations in here. And so the first one that we're going to look at is a nonlinear dynamic simulation. And nonlinear means that my loads can be a function of time, that my material properties, we could look at permanent deflection if we want to, and that we can have sliding contact in our model. So now we're looking at a assembly level stress analysis. Let's take a quick look at an animation of this result. And our deformation scale is 180 times, so to make things look a little more interesting. And we'll be able to see how our kind of cantilevered mechanism here is oscillating due to our impulse load. And I'm using sensors, once again, to track my results at key locations. So the hottest spot in the model is our fillets here, where the clevis comes in. And this transient sensor is looking at my time-based results over all of time and giving me a plot of the maximum stresses on that face as a function of time. So how is this model assembled? Very similar to the tools and capabilities if you do linear static analysis, but we'll start at the top. We see there's check marks next to all of our bodies, which means we have material definitions applied. In addition, since we're in nonlinear, we have a much wider selection of material model selections, plasticity models, hyperelastic models, things like bushings and rubbers, or linear elastic like we use in static analysis. As we walk down our feature manager, we see that I'm using pins to provide my kinematic relationships between the bodies, or rotations. No need to model pins. That would just take up more elements than we need to spend for that. In addition, when we use a pin connector, we can also define strength data and look at the forces through these pins and get a go, no-go on the strength of our hardware. Very similar process for bolts. Now the exciting part about this model, it's going to be different from linear static analysis that you might have done, is that we're defining a basic excitation as a function of real time. And what essentially we're doing is where we have all our fixtures, we're saying we're going to take the part at those fixtures and apply this excitation. So this is 20 Gs in the up direction. And because it's nonlinear, we can define a table. So this is the G load as a function of time. And then we can view our sawtooth waveform. From there, we can choose to apply damping. So I have a low level of damping. We usually look at our first peak, so it's not that critical for this particular analysis. And because we're running multiple time steps, we are able to choose how much data do we save. So if we don't want to use up a bunch of disk space, we're running lots of little small time steps. In this case, I'm saying save every 5th time step to save my disk space. And then from here, we want to look at the maximum stress on the fillet of our linkage, and we're looking around 40 megapascals. And then at the end of this presentation, we'll take a look at our stress values and see which one of these scenarios was the worst case. So this is nonlinear dynamic shock loading.